Okay, we're going to continue our discussion on bearing capacity for shallow foundation special cases. We move on now to bearing capacity of layered soil, weaker soil underlain by stronger soil. So a while ago, we discussed on bearing capacity of layered soil, stronger soil underlaid by weaker soil. So for this one, for this concept, we have here a foundation that is supported by a weaker soil layer underlain by a stronger soil. Of course, we are still on two-layered soil. However, our top layer is a weaker soil and the bottom layer is a stronger soil. So the ratio between Q2 over Q1 as being defined previously will be greater than 1. So for this one, if our ratio of H all over B is relatively small, as shown here on the figure, so the ratio between H all over B is relatively small, so meaning to say the failure zone will be situated or located between on the weaker soil, and it will be seen also on the stronger soil. However, if the ratio between H all over B, the failure surface will be fully located in top on the weaker soil only. So this one, if the ratio between H all over B is relatively high, so meaning to say the failure surface is only visible on the weaker soil, on the top soil. So this is an illustration for a two-layered soil wherein the top soil is a weaker soil and the bottom part is a stronger soil. So as mentioned a while ago, if the ratio between H all over B, as shown on this left side of the illustration, is relatively small, the failure surface will occur basically in both layers. It will occur on the weaker soil and it will also pass through on the stronger soil as being illustrated here. So this is the failure zone. So it extends to the stronger soil when the ratio between H all over B is relatively small. However, on the right side, in the right illustration, if the ratio between H all over B is relatively high, the failure surface will only be visible on the top layer soil, which is on the weaker soil. So this is the failure surface. It will only pass through on the top soil, which is on the weaker soil. So for this one, for that condition, the ultimate bearing capacity can be given by this empirical equation. So you have the ultimate bearing capacity is equivalent to this expression, and this expression should be greater or less than or equal to Q sub T. So D, of course, is the depth of failure surface beneath the foundation on the thick bed of the upper weaker soil. Of course, we know that Q sub T is the ultimate bearing capacity in the thick bed of the upper soil, and of course, Q sub B, that is the ultimate bearing capacity in the thick bed of the lower soil. So this is the equation for the ultimate bearing capacity on the top layer soil, and this is the ultimate bearing capacity on the bottom layer soil. So we have here figure foundation on weaker soil. So this is an illustration for a foundation on weaker soil underlain by stronger sand soil. So this is a variation of, this one is a variation of the ultimate bearing capacity with the ratio of H all over B. So the figure presented a while ago, those are the illustration of the two layered soil having a top soil that is a weaker soil and the bottom is a stronger soil. So this one is the nature of the variation of the ultimate bearing capacity with the ratio of H all over B. Of course, we have to identify our bearing capacity factors to the soil angle friction for the top layer and the bottom layer, and we have to also to identify our shade factors to the soil friction angle for the top layer and the bottom layer. So according to Mayor of Enhana, they suggested that the D should be approximately equal to B for loose sand and clay, and the D should be approximately equal to 2B for dense sand. Okay, let's have a problem. So you refer to the figure presented a while ago. For a layered saturated clay profile, you are given with these parameters. We have to determine the ultimate bearing capacity of the foundation. So we have to identify or solve for the ratio between the bearing capacity for the bottom with respect to the topsoil. So it is 2.08, which is greater than 1, with phi1 and phi2 is equal to 0. So compute our bearing capacity at the top layered soil. So using the equation, we have 7,220.4 pounds per square feet. And of course, for the bearing capacity at the bottom soil, this is equivalent to 14,938.3 pounds square feet. And if you're going to substitute to this equation for the computation for the ultimate bearing capacity, we can have that value, which is 9,225 pounds per square feet, and this is greater than our bearing capacity for the topsoil. So which means that we're going to use D is approximately equal to B. So for this one, since our ultimate bearing capacity satisfies the condition that it should be greater than the bearing capacity of the top layered soil, so our ultimate bearing capacity is 9,225 pounds per square feet. So we move on now to closely spaced foundation effect on ultimate bearing capacity. So if the foundation are placed close to each other with similar soil conditions, the ultimate bearing capacity of each foundation may change to interference effect of the surface, failure surface in the soil. So this was investigated for the effect on the ultimate bearing capacity of foundation that are placed close to each other. So this was investigated by Stuart in 1962, and he used for his investigation, theoretical investigation, a granular soil. Of course, we know that the granular soil is a coarse grained soil. It can be gravel, sand, or silt. There is a little or no presence of clay. So we make use of that type of soil. However, based on the assumption by Terzaghi, he assumed that the geometry of the rupture surface in the soil mass would be the same for the closely spaced foundation. However, Stuart have a theoretical investigation, and he came up with 4 conditions. There are 4 conditions for the 4 conditions. There are 4 cases that he encountered in his investigation on the ultimate bearing capacity of the foundation, depending on the spacing of the center-to-center spacing of the 2 foundations. Of course, that center-to-center spacing of the 2 foundations, according to him, it affects the rupture surface on the soil. So this is the first case. This is the second, third, and fourth case. So this was a study that was conducted by Stuart on the assumption of the failure surface in granular soil under 2 closely spaced rough conditions. So basically, the rupture surface of the soil is highly affected, according to him, based on the center-to-center spacing of the foundation. So these are some of the efficiency ratios, theoretical variations for the efficiency ratios that was came out based on the theoretical investigation. So we move on now to bearing capacity of foundation on top of a slope. So there would be cases wherein we're going to construct a foundation on top of the slope or on the slope itself. So in some instances, shallow foundations need to be constructed on top of a slope. This is an illustration for a foundation that is constructed on top of the slope. So this is the sloping area. We construct the foundation on this portion, and it is being classified as a foundation on top of a slope. So basically, based on Mayer-Off, the theoretical relation of the ultimate bearing capacity for continuous foundation is given by this equation. So for purely granular soil, when C prime is equal to 0, we have this formula. However, if that is purely cohesive, when phi is equal to 0, that is an undrained condition, so we can make use of this equation. Of course, C refers to undrained cohesion. So for this one, we have to identify, be familiar with the parameters present. So we have our H, our beta, our small b, and of course capital B. Of course, you have the ultimate bearing capacity, the depth of embedment. You have other parameters such as the unit weight, cohesion, and undrained cohesion, and of course the angle of friction. So these are some of the bearing capacity factors for granular soil according to Mayer-Off, and this is the bearing capacity for purely cohesive soil. So for the stability number, we make use of the equation gamma times H all over C, and we have this condition when H is greater than B. You have to have the stability number equal to 0. When B is greater or is equal to H, use the curve for the calculated stability number. So you make use of this one. So we have here an equation problem. We are going to compute, we are given with these parameters. We are going to compute for the gross allowable bearing capacity, having a factor of safety equal to 4. So since based on the given parameters, based on the given data, our H is greater than B. So the stability number is 0. So you make use of this equation for the computation of the ultimate bearing capacity. And we are given with the depth of embedment all over our width of the foundation, that is equal to 1. The ratio between B, small b all over capital B, which is 0.67. And of course, from the figure, if beta is 30 degrees, this ratio is equal to 1, and this one ratio is 0.75. The bearing capacity factor is equal to 6.3. So we try to get our ultimate bearing capacity, substitute to this equation, that is 315 kilonewton per meter squared. And if you're going to compute for the gross allowable bearing capacity, you have to divide our ultimate bearing capacity with the factor of safety, and that gives us 78.8 kilonewton per meter squared.